Chapter 11.4, lesson number 2. Continuing on with our examples, we went through the one in the textbook. I highly encourage you to look at that one. But let's do this one step by step, and I think you'll really understand it by the time we've gotten through this one. So here we have one. It says calculate the enthalpy change for the formation of what is known as acetylene or ethine. All right, so we are trying to figure out the delta H for this one. It's a particular formation enthalpy. Okay, and so we want to see if we can figure this one out by utilizing the 3 reactions that we have here. You'll notice none of them are a formation of ethine, much like we had in the last problem. So we do begin with an assumption, okay? The delta FH for the reaction that we're looking for is actually equal to the sum of all of the other reaction enthalpies that we have right there. Okay, so we just have to manipulate and change and put these things into the right spots in order to be able to work with them. So our first one here, and I like to start with the compounds, is to put in acetylene. As I take a look at reaction A, B, and C, I would ask the class here, okay, which reaction has acetylene within it? As you take a look at it, you can see it's only reaction A that can take care of the acetylene for us. So acetylene is a reactant here, but I need it as a product. So I'm going to have to take this reaction and flip it. Okay, so let's do that. I now have 2 carbon dioxides. I have 1 liquid water, and of course that would produce acetylene, C2H2 gas, and we would have 5/2 oxygen molecules. What happens to my delta H because of this one? It changes signs to 1300.2 kilojoules, but it is now positive. Okay, so the delta H of this particular combustion reaction is now positive rather than negative. So we have, in this case, a sign flip. Simply because I wanted this as a product, but my source equation was a reactant. Okay? The proportion of it, 1 mole of acetylene, is equivalent to what I need in my target equation of 1 mole of acetylene. So I don't have to multiply or divide here. The next thing is start putting in all of the other unique and individual things that we have. And so I'll take a look at carbon here. Okay, which of my reactions has elemental carbon within it? As you take a look at these, you can see that, hey, only B has elemental carbon. So we take a look at where we want it. Carbon is a reactant in the source equation. Carbon is a target in the, carbon is a reactant in the target equation. Sorry, my mind wandered there. So it's in the right spot, which means I don't have to flip it. So I take a look at that, and I have carbon plus oxygen is going to yield for me carbon dioxide. And that will give me delta FH for this one of negative 393.5 kilojoules. Now, some of you are already saying, hey, Mr. B, wait, hold on a second. There are 2 moles of carbon needed in my target equation, but I only have 1 mole here. You're correct. So what I will do is I will double this, and if I double the reaction, I also double that particular amount there. So this now becomes, what is it here, 787 kilojoules. Okay, I have one more thing to put in, so I've got in my acetylene, whoops, I've got in my carbon, now I just have to put in some hydrogen. As I look at my equations, we're lucky again in this case, only one thing has hydrogen, so I'm going to have to use C to put in my hydrogen. Hydrogen is a reactant in my source equation. It's also a reactant in my target. It's 1 mole quantity in the source, and it's a 1 mole quantity in the target, which means that there's no manipulation I need for this one. No flipping, no doubling, tripling, or halving. I just have to write it in. So there's my hydrogen gas, my half mole of oxygen, and my 1 mole of liquid water. And that was related to a formation enthalpy of negative 285.8 kilojoules. So now I just want to assess and double check that these changes, because I put everything in, actually does work out to the equation of 2 carbons plus 1 hydrogen gives me 1 acetylene. So let's look for things that are on both sides of my overall statement here. I have 2 moles of carbon dioxide here as a reactant. I have 1 mole on this, but remember we doubled this, so that's 2 moles of carbon dioxide that can cancel out. I have 2.5 oxygens over here. I don't want those in the problem. And so I have 2 moles, because there's 1 here, times 2, plus another half, that's 2.5. So all of my oxygen cancels out, and we're good there. Double check one more thing. I have 1 mole of water here as a reactant, 1 mole of water here as a product. They should cancel. And if I look at what remains, I have 1 mole of acetylene, I have 2 moles of carbon, and 1 mole of hydrogen. So if you look at your reactants, it's 2 carbons plus 1 hydrogen gives us 1 acetylene. Therefore, since I now have my target or my source equation all done here, Hess's law states that the sum of these changes is equal to the formation enthalpy for the reaction that remains for my acetylene. So, positive 1300.2 plus negative 787 plus negative 285.8 gives us positive 227.4 kilojoules. All right, hopefully that makes a little bit of sense. Now there is one other thing I wanted to show you here just to see if we're right. Just a moment. If you recall, we do have a table of formation enthalpies. Okay, what does our table tell us about C2H2? If we go to our table and we take a look at ethine, which is also known as acetylene, there's your C2H2, and it says we get positive 227.4 kilojoules of energy required per mole. So, how many moles did we form here? We formed just 1 mole, so it should make sense that it is positive 227.4. So that's a nice piece of evidence that we have for us to prove that Hess's law truly does work. Okay, go on to one more here. This one's got a little bit more going on. It says calculate the standard molar enthalpy of combustion. So we're looking for delta CHM for ammonia, which is NH3. Okay, that's what we're looking for here. So we do need to show the equation for the combustion of ammonia. And so ammonia, being NH3, in a combustion reaction would react with oxygen, and this should produce for us the most common oxides. Remember, our most common oxides for our nonmetals are the dioxides, so nitrogen and oxygen would be NO2. All right, and then, of course, hydrogen, when it reacts with oxygen, produces water. And in this case, let's assume liquid water. Okay, we'll talk about other reasons why. And we are looking for the delta CHM of ammonia, which we don't have directly. We don't have a combustion table to research, so we have no choice. We'll have to try and use Hess's law to do this. Let's make sure we're balanced before we proceed. There's your 3 hydrogens, that's a good place to, or pardon me, 1 nitrogen, 3 hydrogens, 2 hydrogens. That is a common multiple of 6, so I will triple this amount and double this. That did change my nitrogens, so I'll double this. And now oxygen being the last remaining thing, we want to see how many we've got. So 2 times 2 is 4 oxygens with my nitrogen dioxide, plus another 3 gives me 7. So I need 7 halves of the oxygen molecule to come up with 7. okay? Or 3.5 oxygens if you prefer. So there's our balanced equation. This is what we need to make from our 3 sources. So let's just start putting things in, okay? As I take a look at this, I want ammonia into this, and so I'll check my equations, and only one equation has ammonia. So I'm going to have to use equation A to put ammonia into the problem. Okay, and you can see that it's in the right spot. Both are reactants, so no flip is necessary, but I don't have enough. There's only 1 in my source, but there's 2 in my target. So I will have to double this first one to put in the correct amount of ammonia. To do that, then, I can write this one with all the doubled values, which would be 2 ammonias to produce, well, double that. That would be 1 nitrogen molecule. Double this, that would be 3 hydrogen molecules. And, oops, no extra plus there. And this, of course, would double the enthalpy change. So the delta H, or the delta DH, because we're decomposing ammonia with our source equation, is going to be double that amount, or what would we have here? Positive 91.8 kilojoules given off in this reaction. In the source, it gave off 45.9. The only thing we did was double it, so by showing the doubling in the equation, I get double the energy released. Again, it's that whole 1 match, 2 match idea. The next thing I could put in is oxygen. All right, so let's take a look at our source equations and see what's happening here. No oxygen in the first. Oh, there's some oxygen with B. Oop, there's some oxygen with C. This is a warning. I don't know through Hess's law which of these equations, B or C, or both B and C, are responsible for the amount of oxygen that I have. So if one of your things in the target equation appears in multiple other source equations, ignore it for now. So we got ammonia in here by doing this one. Let's ignore oxygen for now, and hopefully nitrogen dioxide and water vapor are a little bit easier to put in. Let's move over to nitrogen dioxide. I don't see it in A. I don't see it, oh, there it is in B. Okay, and then of course, I don't see it in C. So I'm gonna have to use equation B to put in my nitrogen dioxide. My target, my target equation has 2 moles of nitrogen dioxide as a product. My source equation has 2 moles of nitrogen dioxide as a product, which means the amount is correct and it doesn't require any flipping. So I just have to write it as is. But the energy term's a little bit different. So we want to get it as just a delta H out of this equation. So let's write it so far what we have. You have nitrogen gas plus oxygen gas to produce for us 2 NO2 gases. Okay, so we've got that. What does this tell us about the delta H? I have 66.4 kilojoules required for this equation, and it's written as a reactant. That means it's endothermic. I needed energy before I could make the product. So when I take a look at the formation enthalpy, because I'm just forming nitrogen dioxide, it is going to be positive 66.4 kilojoules. And this takes us back to chapter 11.3, the different ways we can communicate enthalpy. So nitrogen dioxide's in the problem now. Let's take a look at water. How many of my source equations have water? No water in the first, no water in the second. Water is only found in the third equation, and it's the decomposition of water leads to positive 285.8 kilojoules. So I need water as a product. It's a reactant here, so I will have to flip it and change the sign. I also need 3 moles of water as my product. This only has 1. So I will have to triple this one as well. So let's do that, and then we'll see what kind of change we get with our overall enthalpy. So I've got oxygen plus the hydrogen, because I flipped the reaction, so now those are my reactants. And I also have my water. Okay, I now need to triple this amount, so I'm going to have 3 waters, 3 hydrogens, and 3 times a half is just 3/2 of oxygen. So now I have it to the correct proportions. I just have to multiply this flipped value by 3. And so the delta formation of water here that I had is now negative 285.8 because I flipped it times 3 to get me negative 857.4 kilojoules. We can go through and make sure that we have the right stuff in this equation. So as I do that, I needed 2 ammonias as a reactant. I have 2 ammonias as a reactant, so that's good. I needed 2 nitrogen dioxide as a product. 2 nitrogen dioxide as a product, so that's good. 3 waters as a product. There's 3 waters as a product. The only thing I'm uncertain about here is how much oxygen I have. Hopefully, and what should happen in a lot of cases, is this unknown takes care of itself. If it doesn't, then we'll have to keep going. So, let's see what we have here. We need 3.5 oxygens when we take a look at this one. And so, I have, what do we have here? Hold on a second. Knew something didn't look right here. I made a misstep when I was writing this one. This should be 2 oxygens. All right, so let's take a look at our oxygens. I have 2 oxygens here, and I have another 1.5 oxygens here. And so I needed 3.5 oxygens. There's 3.5 oxygens. So lo and behold, it worked out. We just have to see if nitrogen cancels, and I have 1 mole of nitrogen as a reactant, 1 as a product. Does hydrogen cancel? Because I don't want that here. 3 moles and 3 moles. 1's a product, 1's a reactant. They cancel. So when you take a look at what we have created here, we have 2 moles of ammonia plus 3.5 moles of oxygen to produce 2 moles nitrogen dioxide and 3 moles of water. So since we have successfully added and manipulated the source equations to make the net equation, those reflective changes in the enthalpies should end up for the combustion enthalpy for this reaction. And so we'll add positive 91.8 to positive 66.4 to negative 857.4, and that works out to negative 699.2 kilojoules. Is that the answer to our question here? Not quite. Remember, our question was asking us for the molar enthalpy of combustion for ammonia, but this is just the enthalpy of combustion for the reaction. How many moles of ammonia were actually reacted here? 2 moles. So if I want the delta CHM for ammonia, I have to take the energy for my given reaction. All right, negative 699.2. And divide by the molar quantity that I saw related to it. And so that's 2 moles of ammonia. So simplify that, 699.2 divided by 2 ends up to negative 349.6 kilojoules per mole. And that is the answer to our question. Okay, I'm hoping that made sense to you guys. It is a bit of a process. There are a couple of shortcuts that we can take. Remember that any flips must reflect as a sign change between your source equations up here and what you're using to make the net equation. And any doubling, tripling, or whatever you have also gets reflected in the enthalpy changes for the reaction. Again, burn 1 match, it gives off X amount of energy. Burn 3 matches, it gives off 3x the amount of energy. Okay, so it's all related to quantity. There you go, there's the 2 guided examples. There's a few more in the textbook. Make sure that you are going through and reading through 502 to 509, at least peruse it for the examples. That would be very important. Try practice questions on 504 and 508. There is Lab 11B and Lab 11C. Those ones are really quite good. Take a look at those. And there is a very important problem to look at, number 11 on page 508. All of these things should be done before you start taking a look at Lab 11.3, in which we'll have a chance to go take a look at this Hess's Law process and make sure that it works out. Okay, sorry that one was a little bit lengthy, but lots to explain with Hess's Law. Try these out. Hopefully it's working well, and good luck with it. We'll see you guys in the next video.